Bismillahirrahmanirrahim. In the previous class, we were talking about the different characteristics of a discrete signal. We have talked about the periodicity of the discrete signal, and also we have mentioned that discrete time sinusoids whose frequencies, this frequency means that the discrete frequencies are separated by an integer multiply of twice pi are identical, which means that if we have omega 1 and omega 0, where omega 0 plus twice pi is equals to omega 1, or if you have another frequency like omega 2, which is like omega 0 plus 4 pi is equals to omega 2, in all the cases, they are identical. That means omega 1 is identical to omega 0 and omega 2 is identical to omega 0. That means they are identical. That means omega 2 is identical to omega 0 and omega 1 is identical to omega 0 as well. So what does it mean? We have already mentioned in different way. However, we'll try to give some more explanation on that. Before starting to that, if you have any question from the last lecture or lectures, if you have any sort of question, you can raise your hand. We can discuss on that. Afterwards, we can move forward. Probably I will try to wrap up all the stories of the discrete time signals properties today, so that you can learn it. Our one of the main objectives is to understand the representation of the discrete signal in the frequency domain as well. So today we'll also talk about this. Yes, 34.
Sir, I had a confusion regarding the term identical. Sir, are there different in the discrete domain but identical in the analog domain? You mean that, right?
Okay, so I'll give that explanation, inshallah. So that is one of the main objective of today's lecture. Identical means you feels like they are same. They are not the same. That is called the identical. Okay, so you feel that okay, it's like the same, but it is not the same. So you have some input. You know that what is the input, but at the end of the day, whenever you got the output, you found that that is something different. So then you thought that okay, this output is identical to the input. They are not equal, but they are identical. So I'll give the example. Thank you for the question. Any other question? Yeah. Any other question? Okay. If not, then please follow me. Inshallah, you will find the answer. Okay. By these characteristics, that means if I try to show you the things like I have already mentioned, like y1 omega 1 is equals to omega 0 plus twice pi. We have already mentioned it. So how we can prove that? Okay. So we have wrote it like that. This is a cos omega 0. Then we are adding twice pi. This is n and then theta. So then we have wrote it like cos. What is this? Cos omega 0 plus twice pi. That is actually omega 1. So we start with omega 1 and we have found that this is omega 0 n plus twice pi n plus theta. And you know that cos twice pi n, where this is n is an integer value, any value for n, you'll find that it will gain the same result. So that's why we can write it like cos omega 0 n plus theta. So which shows that what is the discrete frequency of this part? What is the discrete frequency of this one? Of course, by the formation, you can find that this is omega 0. And what is the discrete frequency of this one? That is, of course, omega 1. So you start with omega 1, and unfortunately or fortunately, you are end up with omega 0. What is the difference between these two? The difference between these two is twice pi, or it can be a multiplications of twice pi. So you can write k into twice pi. So any frequency omega 0 plus k twice pi, and they are identical, where the k is equals to 1, 2, 3, and any integer value like this. So this is by the definition, and this is by the mathematics. You can prove it. Now, what does it mean by this in the frequency domain point of view? Try to understand it from the frequency domain point of view. This is in the scale of omega. That means the relative frequency in radian in the discrete domain, and that is the amplitude of each component. Let's say this is your omega 0, and where should be omega 1 to make it identical? Of course, we have already mentioned omega 0 plus twice pi. So let's say I'm making scaling before writing omega 0. I can make this is pi, this is twice pi. Okay, this is minus pi, this is minus twice pi, something like this. Okay, now where is omega 1? Omega 1 is omega 0 plus twice pi. So where is that twice pi? If I want to extend it in the right side, let me erase this part. Extend it. So this is thrice pi. Of course, try to understand this is in the scale of omega. This is 4 pi. So you can write where is omega 1. So twice pi. So this is 1 pi, and this is 2 pi. So after twice pi, you have that. So yeah, is that fine? Are you with me?
Yeah. Yes, sir, it's fine.
Yeah, fine. So you are adding that value, and you have found that, okay, that is the position. This is the position. Okay, I'll just make a stem of that. This is omega 1, and this was omega 0. So according to the formula, we have found it. Okay, they are identical. And now, if I draw the things like before, that means it shows that from minus pi to plus pi. Let me draw it like this. So this is, what is the distance? This is also twice pi. So if I have something over any point of this triangle, we have the same thing. Actually, it will repeat under the umbrella or under the triangle of pi to thrice pi, isn't it? Because we have already know that any frequency could be identical with omega 0 plus k twice pi. Here this omega 0 can be mentioned as the baseband frequency. That is the fundamental frequency. Okay, that is the baseband or the fundamental frequency. So now, if you understand this, the omega 1, if you start with omega 1 in the reverse pattern, if you start with omega 1, you can find something that is identical to omega 0. And what is the value? Of course, you have two identity of a frequency. One is in the discrete domain. So it belongs to, this omega 1 belongs to, let's say, f1 divided by, let's say, capital F1 divided by fs. And this omega 0 belongs to f0 divided by fs. So how could we find that statement, f0 divided by fs and f1 divided by fs? Okay, let me introduce this first. From the analog signal, try to follow me. Analog signal, what we can write. So neglect the value of a. Okay, a cos omega t plus theta. I start with very beginning. And then when we have moved it from the analog domain to the discrete domain, we represent it like this: A cos, now this is omega 0 n plus theta. If I elaborate the value of omega, capital omega, let me draw it here. What is capital omega? Capital omega is twice pi capital F. Okay, twice pi capital F, and then we are putting the value of t. Let me write it like omega, only omega, not omega 0, just for making it in general sense. Okay, and now in the discrete domain, what we have wrote, this is cos, what is omega? Twice pi small f n plus theta. Now concentrate on the term n and f. What is n? We have mentioned that whenever we have the value t, capital T, small t, the time, it can be represented as the number of samples with the capital T, where the capital T is the sampling time. So the 2 points, okay, for the 2 samples, you have several samples. What is the distance between these 2 is the t value. Then what is Fs? What is Fs? Can you please reply? What is Fs?
1 by that t value.
1 by t. Yes, thank you. So then we can write this t is equals to nothing but n into 1 by Fs. So now you can replace the value of t with correspondence of n and Fs very easily. You can represent that. Okay. So let me write it in that way. So we are writing xat is equals to a cos, that was twice pi capital F, because we are talking about the analog signal, capital F t plus theta. Now it can be write as cos twice pi f. What is t? Small t is equals to n into t. Please try to understand the things, because it will be very, very important for the application. 1 divided by Fs, so we can write n divided by Fs plus theta. So you can write like this: twice pi f divided by Fs into n plus theta. So this is nothing but what? Now, apart from t, we have n, so we can write it xn. We can write it like xn. This is an analog signal, and this is also an analog signal in the discrete pattern. Discrete, that's why we have n. Don't think that this is a digital yet. Okay, and we can write it like this: xn is equivalent to xat. Why they are equivalent? They are not equal, because as you can know that t is a continuous one. When t is continuous, that means that you have all the values. But what about xn? If you are taking this t value very low, if the t value is very low value, then this xn is very close to xat. That means you may have almost all the data from xat if you have a very high sampling frequency. But if you have a general average sampling frequency, definitely you are missing some data. That's why I'm writing like this: equivalent, or sometimes it can be written as like this. There is three lines. Okay, so these are the notations. Now I believe that you understand this point, and we can also write it in this way: xn is equals to a cos twice pi small f n plus theta, isn't it? So we can write it like this.
Sir, can you repeat the last part again?
The equivalency part.
Yes, sir.
Okay. The equivalency part can be written like this. Okay. So XAT has all the value, like this is a continuous one. You have a continuous one. But what about XN? You have some samples. You have some sample data. If I write the line, so you have some sample data. Now, if you increase the sampling frequency, it can be very close to XAT, but it will never be like equal. You have all the value inside XAT, but you have some set of data inside XN from XAT data. So XN is a subset. XN is a subset of XAT. So that's why we can say this is equivalent. Is that okay?
Yes, sir.
Okay. And now, yes. So from this equation, equation number 1 and equation number 2, what we can say? We can say that the small f is equals to nothing but f divided by fs. We have another representation, so this is very important. So please mark it. The small f is equals to capital F over fs. Okay. So what is a capital F? So I can write it. Small f is equals to f over fs. Now, what is capital F? What is the name of the capital F?
Analog frequency.
Exactly. So analog frequency. Need to understand. And fs is the sampling frequency. Sampling frequency. This is a very important statement. Similarly, we know that the omega is equals to twice pi f. So we can also write omega equals to twice pi f divided by fs. Okay, so these are the very simple things. So please remember this part. This will help us. Okay. Do you have any ambiguity over there? No. So what we have learned, the t, the time in the continuous domain, can be represented n into t, where t is equals to 1 by fs. So anytime t can be replaced as n over fs. We can replace it. So this is one relation we have learned, and also we have learned small f is equals to f over fs, where fs is the sampling frequency and capital F is the analog frequency. Okay, and now jump to that previous example where we have learned about the relation between omega 1 and omega 2, omega 0, something like that, 3 pi, 4 pi, minus pi. This domain is very important for understanding. So what we can start with, let's say this is our omega 1. And what is omega 1? This is related to twice pi f1, and that is equals to twice pi. What is f1? Capital F1 divided by fs. If you found anything ambiguous, please raise your hand. Okay. Now, where is their alias, or you can say the identical signal? According to the properties, we have found that the omega 0 could be is equals to omega 1 minus twice pi, because omega 1 is equals to omega 0 plus twice pi. So where is that? And we have found it. Okay, this is the point. Okay, this is your omega 0. Now what is omega 0? Omega 0 equals to twice pi f0, and twice pi f0 is equals to again twice pi capital F0 by fs. Now who are identical? Who are identical?
Omega 1 and omega 0.
Exactly. In the digital domain, omega 0 and omega 1 are identical. And in the analog domain, in the analog domain, real domain, the F0 is identical to F1, where this is called alias. This is called aliasing signal. Why this is alias? Okay, we'll give some example. We have already given some example, but still we'll talk about that in the later part. So if you give the value of F1 to some system in a discrete system, and after having the discrete system converted to the analog again, if you got some signal like F0, for example, if F1 is equals to 10 kilohertz, you are putting this 10 kilohertz to a system. What kind of system? The digital system, digital signal processor. Okay. And after that, if you found that your signal is converted as an analog signal, and you'll find that, okay, it looks like 1 kilohertz, then 1 kilohertz is the alias of 10 kilohertz, is the alias of the 10 kilohertz. Okay, so that is the term we have used for the aliasing of the signal. Okay, now by choosing different color, I try to make you understand that if there is another signal at this moment, where is the identical one? Before twice pi. Before twice pi. So that means it is very close to this. Try to understand each and every point with a different color. With a different color. If I put some frequency over there, where is the identical one? This is the identical one. If I have another color, putting another signal close to this, where is the identical signal? You'll find it before twice pi, and this is the identical one. Not only there, you can also find some identical signal after twice pi as well. So what I mean, you'll find some identical signal after twice pi as well. So by this, what I can try to make you understand, let me choose the black color. Whatever you have after twice pi to thrice pi, whatever you have there, you have the same thing inside minus pi to twice pi. You have learned it. Okay. So inside the minus pi to plus pi, whatever you have the repetition between pi to thrice pi. So what is the space? Pi to thrice pi, this is twice pi space. And again from minus pi to plus pi, you have also twice pi. And these sequences or the frequencies are known as the baseband. The frequency belongs to minus pi to plus pi is known as the baseband signal, because those are the original signal and other one are the signals by which you can find the alias of the signal. We'll give the example, but by this frequency domain analysis, we should understand this. Why we are putting this kind of diagram all the way through the courses, okay, on the signal and system and telecommunication. So we are putting like this kind of pyramids or triangles. Why we are putting that? Because all the things what you have there, you have the same thing inside this. So if you want to analyze this part, it is better to analyze this part because it will also give some advantage of lower part of the frequency. You have the low frequency over there. Okay. Okay. Now, if I ask you one very basic question. Let's say we have a cause signal. Okay, so we have a cause signal. Now we are putting some samples. So let's choose a sampling frequency. How to choose the sampling frequency? According to the Nyquist theorem, you know that. What is the Nyquist theorem? Any of you? Yes. You need to raise the hand. 115. Yes. Continue.
The sampling frequency must be at least twice that of the signal frequency, minimum signal frequency.
Okay. Otherwise, what will happen?
Otherwise, it will be hard. It will not be possible to reconstruct the signal from the sampled signal.
Okay. Yes. So otherwise, you can't reconstruct the signal. That is the problem. Okay. So let me introduce the thing. So if this sampling frequency, what is the sampling frequency here? The sampling frequency, let me choose that. Okay, this is the full cycle. If this is a 1 second, this is 1 second. In 1 second, we have a full cycle. So the frequency of the signal is 1 hertz. So what should be the sampling frequency? Minimum, that should be 2 hertz. So we can put those samples, 2 samples at least. So we need to put 1 samples there and another samples there. Okay, so at least 2 samples. In the next cycle, 1 sample and 2 sample. In the next cycle, yes, we know that. So how it should be, those are the samples according to the Nyquist theorem. Why those are necessary? Because if I give the samples to the analog to digital to analog converter, what I mean, if I give those samples like sample number 1, 2, 3, 4, 5 to the digital to analog converter, in the output, whatever the analog signal will find, what is the frequency of that analog signal? If I put only those samples to the digital to analog converter, so those samples are given as an input and the output would be an analog signal. What should be the frequency of that analog signal? What could be the frequency of that analog signal? Any of you? How could you find that? The digital to analog converter, that will be a sampling and hold circuit. That means output. In the output, I have already mentioned that there is a capacitor. So that means that will just make a straight line like this. Okay, you can say that, okay, it might make something like that. The green lines, it will just proceed to that one. Okay, this is not exactly like this, but ultimately you will get something, some data like that one. So what is the frequency of this green line? What is the frequency of that green line? Yes, 34.
So it will be the same, sir. The same 1 hertz.
Exactly, this is 1 hertz. So can you retrieve the signal back from the frequency point of view? What could be the answer?
Yes, sir, it can be.
It can be. So before putting the sampler means I could like to say the analog to digital converter, the input frequency is 1 hertz. After analog to digital converter, you are putting digital to analog converter. What is the output? Output is 1 hertz. So that means you can retrieve your signal back. You can retrieve your signal back. So you don't have any aliasing. Now, if I have we are putting some samples like this. So at the beginning, we are putting some sample, and let me put over there. And some other point is there. Okay, so let me complete this over this. If the sampling period is now higher, this is the second case. So you are putting some sampling frequency. What is the sampling frequency? We'll find it later on. So it will looks like this. It will looks like this. Now, of course, this output should be equals to 1 hertz or less than 1 hertz.
So less than.
It's less than it is less than 1 hertz. Less than 1 hertz. So you can't get back your original signal. You can't get back your original signal. So for this reason, what should be the minimum samples you need? Number of samples you need for a sinusoidal or a sinusoidal signal to preserve the original signal. So how many samples at least you need for a cycle to preserve the original signal back? I need at least this sample. Okay, so let me give you some example here. If I have this much of sample, just quick response. I will ask the quick response from you. If I have this much of sample, can you retrieve the signal back? Yes or no?
Yes, sir.
Yes.
Yes, sir.
Yes, you can. So if I have this amount of samples, if you have this amount of sample, can you retrieve your signal back?
Yes, sir.
Yes.
Sir.
Yes, sir.
Now, if you have this amount of sample, can you retrieve your signal back?
No,
No, sir.
No.
No, sir.
Yes. So that is the thing. So you have also learned from in different perspective. That means you need at least 2 samples per cycles to retrieve your signal back. And that is the maximum limit. That is the maximum limit of F to retrieve your signal back. Otherwise, there will be some aliasing. So this is a very important statement. What should be the maximum value of F to retrieve your signal back? That is 1/2. 1/2 means we have already mentioned that this is a full cycle. For a full cycle, how many samples you need? 2 samples. So that is by definition F is equals to 1/2. If you have F is equals to 1/4, very good. If you have F is equals to 1/8, very good. 1/16, excellent, and more and more. But what is the limitation of that? If you increase the samples, the limitation is you need to store a lot of data for sampling. So you need to make a trade-off between the quality of the signal you want to retrieve back, and you need to and what is the data processing storage you have for that signal. Okay, so we already found that what is the maximum limit of F for a particular signal. I believe that you all understand this point. Now, if I ask you some question like this, if I have a signal XAT where the frequency is from 0 to 8 kilohertz, you have a lot of signal inside XAT. What should be the sampling frequency? What should be the sampling frequency for that?
Sir, 16 hertz.
16 kilohertz.
At least 16 kilohertz. That means we need to target the maximum frequency of a unknown signal. So this is our unknown signal. we need to target the maximum frequency to sample it out. Otherwise, the 8 kilohertz signals will not be sampled properly. Okay, so let me give you the example here. This is very important. I will show both the time domain and the frequency domain side by side. So let me give you, this is F. F means analog frequency, and this is the strength. This frequency, this F, what is the range of F? The range of F is from -infinity to +infinity. That is the range of capital F. Now, what is the range of XAT? The range of XAT is from 0 to 8 kilohertz. 8 kilohertz. They are original frequency. They are original frequency. Let's say that the 0 hertz, that means DC value has a higher strength, and the 8 hertz has the lower strength. Okay, so this is the signal frequency. And if it is like this, in the negative domain, you will have, that means the -8 hertz, you will have the same thing. We'll talk about the negative frequency afterwards. Okay, let me talk about this 0 to 8 kilohertz. Now, please help me to write it down. Now I just sample it with 16 kilohertz. I sample it with a 16 kilohertz and try to draw the spectrum of small f. What is small f? Don't forget, small f is equals to f divided by fs. So can you give me the value for 8 kilohertz? What should be the value of small f?
Half.
Half. Okay, very good. So probably everybody can understand this point. So it would be half. So this is the point half, and that belongs to, that actually reflects the value of 8 kilohertz. What is the value of small f for DC value? That should be 0 divided by fs. What is that? That should be reflected. That should be reflected to the origin of that one. So this one would be reflected to the origin of that one. So all other points will be reflected accordingly. So we'll have the same values we are replacing in the discrete domain. Similarly, to the left side, that can be replaced like this. And what is the negative value? Negative maximum is -half. Okay, so this is in the scale of f. Now, if I want to make it in the scale of omega, what should be the value? What should be the value? Replacing half.
Pi.
We know omega.
Pi.
Yeah, omega is equals to twice pi f. So twice pi multiplied with half. So you can find only the pi. Very good. And the -half will be replaced as the -pi. Okay, very, very good. Now, the second part. Okay. Now we are choosing. So what was our sampling frequency before? Our sampling frequency was, for this diagram, the sampling frequency fs is equals to 16 kilohertz. Now let me choose the sampling frequency is equals to 8 kilohertz. Now sampling frequency is equals to 8 kilohertz. We want to, for 8 kilohertz, let me take another color, sampling frequency 8 kilohertz. We want to draw the same diagram, this diagram, with respect to sampling frequency 8 kilohertz. Can you let me know where these 8 kilohertz should be placed with respect to small f?
Sir, 1.
1. So f is equals to f by fs. Always very simple formula. F is equals to the highest frequency is like 8 kilohertz divided by fs is equals to 8 kilohertz. So it is equals to 1. So it will be like here. So this is 1. And what is the minimum value? What is the DC value? Of course, always 0 divided by fs is equals to 0. That means you have the profile like this. Now the profile is like this, and this profile is like this. I believe you understand this point. And in the scale of omega, what is this? This is, of course, twice pi, and this is minus twice pi. Okay? Are you with me?
Yes, sir.
Okay. Now your task is to find in the discrete domain, let's say in the discrete domain, this is okay. Let me make it more convenient for us. In between this means what is the value? This is half.
3 by 4.
Huh?
So 3 by 4.
3 by 4. Okay, that means 0.75. So 3 by 4. F is equals to 3 by 4, or omega is equals to twice pi 3 by 4. That means 3 pi by 2. What is the identical signal of that? First of all, what you need to find? You need to find what is the identical signal both in the discrete domain and what is the alias signal in the time domain. First of all, you need to find, so let's say this is your omega 1. So you need to find the value of omega 0. Good. Find the omega 0 first and place it on the spectrum. And afterwards, you need to find the analog signal, which looks like the alias of that. So I believe that you have pen and paper. I'm giving 1 minute to execute this operation. So what is omega 0 you have found? Omega 0 should be, okay. Okay, what is the formula? Should be omega 0. Omega 0 equals to omega 1 minus twice pi. Yeah. So you can place it. So what is the result? Just let me know.
So minus pi by 2.
Minus pi divided by 2. Can you place it somewhere else? This is the point at minus pi by 2. This is 0 and this is pi. So the pi by 2 should be in between, isn't it? At this point.
Yes, sir.
Yeah. Omega 0 equals to pi by 2. What does it mean by that value from the point of view of f? Omega is equals to twice pi into f. So f is equals to omega divided by twice pi. So omega is equals to pi by 2 divided by twice pi. So you'll have 1 by 4, isn't it? So this point is 1 divided by 4 minus. If any of you can't understand the thing, I would like to repeat the things again and again, because this is very important. If you can understand this, you can believe me, you have understood 50% of the DSP, because always we'll jump from the time domain to the frequency domain. And always you need this because we are doing discrete signal processing or digital signal processing. Okay. So what was our concern? our signal band was from 0 to 8 kilohertz. We haven't changed that. We have choose our sampling frequency as 8 kilohertz, and we have found this spectrum, the green spectrum. What I was asking, that the signal in the place of 3/4, at the location of 3/4, or in the omega scale 3π/2, this is 3π/2, what would be the allied signal or the similar signal in the frequency domain? So you have already found that, okay, it should be situated at the location of -12, or you can say -π/2. Both are the same. They are in two scales. Okay. What is the distance between these two omega? What is the distance between these two omega? This omega and this omega?
Twice pi.
Twice pi. What is the distance between these two f? 3/4 and 1/4. What is the distance?
One.
-1. Okay, you should also remember this. So the distance for 2 omega is twice pi, and distance for f is 1. For what? For the repetition, for the similar signal. Okay, now we are at this point where we are at the location of -π/2. Is there any other signal like this -1/4? Where we can
+1/4.
exactly +1/4, because -1/4 and +1/4, they are the same signal. So +1/4. Now 1/4 means in the omega scale what? This is π/2. They are the same. So the first answer, we have got the first answer. What was the first answer? We were looking for the value of omega and the f in the frequency domain, and we have found that. So I can write it here. So the omega, we have found that you can say omega 0 is equals to π/2. From where we have got that, the omega 1 was given as 3π/2. So from there you can find omega 0 is this, as well as we have found f0 is equals to 1/4. Now can you find the actual analog frequency? What I am talking about, what is f0? What is f0?
So the analog frequency, sir.
Exactly, analog frequency. We have the relation between analog to f0. We have the relation, isn't it? f0 is equals to f0/fs. So what is the value of fs? What is the value of fs? For the green case, that was 8 kilohertz, isn't it? 8 kilohertz.
Yes,
and what is the value of f0? Small f0, 1/4. So from there you can find the capital F0. That means the original frequency is equals to what? 8/4. That means 2 kilohertz. What was the actual frequency? What was the actual frequency? That means F1. What was the actual frequency? F1, can you find it?
8 kilohertz.
No, that is not 8 kilohertz. You need to find it. You have small f1, you have fs. So you need to find what is the value of capital F1. What is small f1? This is 3/4. We have mentioned this.
Sir, capital F1 is 6 kilohertz, I think.
So let me write it like this. So F1, sorry, small capital F1, small f1 is equals to capital F1 divided by fs. So capital F1 is equals to F1 is equals to 3/4 multiplied with Fs is equals to 8 kilohertz. So it is equals to 6 kilohertz. So let me clear it up here. Okay. we have started with Fs is equals to 8 kilohertz, and we choose a point F1. We choose this point as 3/4, which shows us the capital F1, the original frequency is 6 kilohertz. But at the end of the day, what we have found that we have F0, we got F0 is equals to 1/4. They are similar. When we got F0, the actual frequency, we found the actual frequency is equals to 2 kilohertz. What does it mean? If you use this kind of sampling frequency, in that case, this 6 kilohertz looks like 2 kilohertz after making analog to digital conversion. Again, if you choose this 8 kilohertz practically for a signal which has a band from 0 to 16 kilohertz, which has a band from 0 to 16 kilohertz, this is the original signal XAT. It's a multiple frequency signal. If you sample it with 8 kilohertz, definitely you know that you are beyond the Nyquist theorem. So you are not abide by the Nyquist theorem. So what the problem could happen? It happens that the 6 kilohertz looks like 2 kilohertz. 6 kilohertz looks like 2 kilohertz, and that makes a problem. Definitely, it makes a problem. And this is called the alias. So the 2 kilohertz is the alias of 6 kilohertz. If I give you the same example for another input, let's say for this green line, that means for 8 kilohertz sampling frequency, if F1, capital F1 is equals to 5 kilohertz, please write it, 5 kilohertz. Take capital F1 is equals to 5 kilohertz. Could you please find the alias signal for this? You have 3 minutes to find it. Should I need to repeat the question? Have you got all the informations? The informations are: number 1, the signal frequency is 0 to 16 kilohertz. Number 2, the sampling frequency is equals to 8 kilohertz. Number 3, your F1 is equals to 5 kilohertz. Now you need to find what is the alias signal of this 5 kilohertz. Let's say there would be some alias. First of all, you need to find whether there is an alias or not. And whenever you found that, okay, yes, there is an alias, then what is the alias signal? Yes, 92, do you want to share something? First of all, first question, do you have any alias signal for this?
Yes, sir.
Why?
Sir, because the Nyquist frequency is definitely greater than 8 kilohertz.
Yes, according to the Nyquist theorem, if the Fs is more than 10 kilohertz, more than or equals to 10 kilohertz, then there would be no aliasing of this 5 kilohertz. However, that is not equals to 10 kilohertz, less than 10 kilohertz. So we should have the alias signal. So now what should be that? So I'm talking about F0. Please find the value of F0. I believe you are doing that. Okay, this was from the omega scale. This is twice pi, that was pi, this is minus pi and minus twice pi. From F scale, that was 1, this is half, this is minus half, and this is minus 1. Where is F1? F1, so small f1 is equals to capital F1 divided by Fs. So
Sir,
you can do it.
F0 is 3 by 8.
That is, so F0 is 3 by 8. Is that 3 by 8 kilohertz?
Yes, sir.
Okay, kilohertz. So you have mentioned that this is 3 by 8 kilohertz. Okay, let's see. So how could we find that? So F1 is equals to F1 divided by Fs, the 5 divided by 8. So that is the ratio. Okay, so we need that. Now we can find already very easily that after 1, it will be repeated. So we can find F0 is equals to nothing but 1 minus 5 by 8.
Sir, F0 is 3 by 8 and capital F0 is 3 kilohertz.
Capital F is equals to 3 kilohertz. Okay, yeah. So we have 3 kilohertz. It seems good. So F0 is equals to what? You can find 8 minus 5 divided by 8. So that is 3 by 8. Because before or after 1, you will find this value. You can do it like this. The 5 by 8, of course, 5 by 8 minus 1. That is also fine. You will get a minus 3 by 8 and make it plus 3 by 8 because they are the same. Because you need to know that why they are same, because the minus frequency and the plus frequency are the same. So you'll find that this is 3 by 8. Now this 3 by 8 is the 3 by 8 is F0 is equals to F0, capital F0 divided by Fs is equals to 8 kilohertz. So kilohertz. So now we can find it very conveniently that F0 is equals to 3 kilohertz. Yes, you are right. So you start with 5 kilohertz somewhere else and you are end up with 8 kilohertz. So what does it mean? Let's say this is your channel. This is, you are putting XAT with a signal from 0 to 16 kilohertz. What is the sampling frequency? Fs. You are taking not 16, 8 kilohertz, unfortunately. And so this means that this is a analog to digital converter. And now after that, you are putting this to the digital to analog converter. Digital to analog converter. The 16 kilohertz. So what would be the range of the output? Tell me, what could be the range of the output from 0 to?
So 0 to 4.
Half of that. What what could be the position of 16 kilohertz? What should be the alias of 16 kilohertz? Because the highest frequency is 16 kilohertz. Let's say F1 was 16 kilohertz. If F1 is 16 kilohertz, Fs is equals to 8 kilohertz. We're talking about the highest one. The lowest one is 0, so that should be comes to the 0 value, no problem. What about 8 kilohertz? Sorry, 16 kilohertz. What is the value of small f1? Small f1 is equals to f by fs. Yes, this 2. Now what is f0? 1. Is it fine? Because before or after 1? Before or after 1? So f0 is equals to 1. Again, f0 is equals to capital F0 divided by fs. What should be the value of capital F0?
8.
8 kilohertz. So that is the maximum frequency folded back. Maximum frequency having its alias, and that alias is of course 8 kilohertz. The maximum frequency you contain in the frequency domain should be the fs. The maximum frequency contained to that is the alias frequency is now 8 kilohertz. Is that it should have we make any problem over there? Because if it should not be 8 kilohertz. Probably I have made some mistake. Okay, let's start with the first. If this is 16 kilohertz with sampling frequency fs is equals to 8 kilohertz, then what is the value of f1? F by fs, that is 2. Okay, this 2 means what? Okay, so it needs some description as well. So this 2 means this is 1, this is 2. This 2 means from the 2 you will have in the 1 and 1 to 0. So this f0 is equals to 1. Eventually it can be also 0, and if that is 0, the f0 could be also 0. That means it is a DC value. So the 16 kilohertz basically folded to DC value. So you start with 16 kilohertz, but it is folded back to the DC value. Of course, you have mentioned the right thing. It would be from 0 to 4 kilohertz. The range would be 0 to 4 kilohertz. We'll describe it in the next class, inshallah, how it will be between 0 to 4 kilohertz. But your task again, if f1 is equals to 16 kilohertz, if f1 is equals to 16 kilohertz, try to find the alias signal of that. Whenever we are talking about the alias signal, that should be inside your original baseband. Where is the baseband? Between -1 to +1. That is your baseband from the f point of view, or from the omega point of view, from -pi to +pi. What is the baseband? So the 2, whenever we are talking about this f1 is equals to 2, that is at this point. Please mute your mic. Yeah. So this is 56. Yeah. So you are there. So that means it was replicated at this point. Is that okay to you? It will be replicated at the point of 1. Is that fine?
Yes, sir.
Yes. Again, that will be replicated where? At the DC point. So that will be replicated over there. That means the f1 is equals to 16 kilohertz looks like f0 is equals to 8 kilohertz as well as 0 kilohertz. So which one will take? We'll take the baseband signal, that is 0 kilohertz. So it looks like the 0 kilohertz. What about if f1 is equals to, let's say, 4 kilohertz? If it is a 4 kilohertz, what will be the value? What is the alias of this 4 kilohertz? Do you have the alias of that? Do you have the alias of that?
No, sir.
No, because in that case, F1 is equals to 4 kilohertz divided by 8 kilohertz, that is half. Where is the half value? We already know that if it is on the half or less than half, in between minus half to plus half, that is the baseband signal. That is the baseband signal, and that's why we are getting the signal 4 kilohertz as it is. Let me clear it up. This is the end portion. We are at the very end portion. If it is like half, 1, this is like 2. What was the example? Minus half, minus 1, and minus 2. So for F is equals to 16 kilohertz and Fs is equals to 8 kilohertz, what we have done, we have shown that this is the value for 16 kilohertz. It is folded out before 1. This is the value, or you can say this is a pi. This is a twice pi, and this is pi. So it is folded there. Is that in the baseband? No. Still, it is not the baseband. You need to fold one more back, so it will be folded there, and this is the DC value. So it will give you the DC value. What about F is equals to, if F is equals to 4 kilohertz, what will be happening? If this is a 4 kilohertz, so where is the place of F? So F is equals to 4 divided by 8, that is half. So that means it is at this point. So you don't need to fold it back. If it is folded back, it will be at the minus half. So that again fold it back to the plus half. So it will remain the same. So 4 kilohertz could be the highest frequency you can preserve. Yes, of course, by 8 kilohertz sampling frequency, you can preserve 4 kilohertz. Straightforward, you can say, but by the diagram, you can say in this way. So the 4 kilohertz can be preserved. So which value? So from 0 to 4 kilohertz you can preserve. What about more than 4 kilohertz? If it is more than 4 kilohertz, what happens if that is more than 4 kilohertz? So 0 to 4 kilohertz, they will preserve. So all the signal, if we have something here, it will be jump back to this place. And again, you will find that it will come back to this place. Okay, we'll start this session, this conversation in the next class. Okay, so before just stopping this, just let me describe this. If we start with a signal here, where it will be jump back before 1. So where is that place? It will be at this place. Is that fine? One of you, please. Is that okay?
Yes, sir.
So this will go back to this, and this is whatever the value, like say minus P, will have the same value as plus P. So it will come back again, and you'll find that this signal corresponding to this, whatever the value of F0, is the alias of the corresponding of this value of F1. Okay, I believe that is fine. I don't have any time to extend more. So thank you for your participation. So we'll answer if you have any question in the next class, inshallah. Thank you.